Welcome to lesson 36 of the course on industrial automation and control. In this lesson, we are going to look at embedded systems, which are basically programmable electronic systems, have had wide applications in various kinds of technologies, including industrial automation. So, a lot of industrial automation products and systems are finding embedded systems in them. Therefore, this lesson is meant to give a basic introduction to embedded systems for industrial automation, how they work, what they contain, what are the basic principles, etc. So, the instructional objectives are the following. First, the role of embedded electronic systems in industrial automation, how the various products and systems and equipment and machines are using them. Then delving into the nature of the technology, what are the typical components in it, what are the typical methods in which these embedded systems are. For industrial automation, they are basically computing systems which interact with the outside world. So, what are the basic methods of communicating with external devices? They are programmable processor based systems, so they contain software. So, some of the basic main features of embedded software, and these softwares, after a certain complexity, you have to have these softwares run under the umbrella of another software called the operating system. So, in this case you use a real time operating system. So, give you an introduction to that, and finally, there are many things that a device needs to do, everything in proper time. So, scheduling, that is when which computation will go on in the system, determining that is actually very important. So, this is called scheduling, and we will look at two typical scheduling strategies used in such systems. So, first take a look at how embedded systems is becoming very important for industrial automation. Typically, production technology involves numerically controlled machines, and they are computer numerically controlled. Sometimes they are directly numerically controlled from a computer, many machines using some communication mechanisms. Then there is process control. If you see if you go to the process control, big process control or process automation company sites, you will find that they advertise, apart from the conventional things, they advertise a lot of embedded system components like smart actuators, smart sensors, intelligent distributed process control systems. All these use embedded systems. Then in manufacturing, people use vision systems, camera based systems for inspection, for safety operations. They use robots, automated material handling systems like automated guided vehicles, automation of heavy movements like cranes and things like that. So, each one of these involves contain embedded systems in them. Finally, today we talk about flexible manufacturing systems, which is nothing but a system which causes coordination between such machines which are quote unquote intelligent, means that they can examine signals, they can look at their environment, they have some amount of computational intelligence, and so coordination is possible, and therefore through coordination better productivity, better efficiency is possible in such systems. So, enabling, if you take a look at that, say the DNC is something which is so here you have a DNC computer, and these are the individual machines. So, MT means a machine tool, and MCU means the machine control unit. So, the machine control unit itself is an embedded system which will typically today contain more than one microprocessor based electronics, and and if you and in a direct numerically controlled system, the several machines are controlled from one computer through a network, right. So these MCU units are typically embedded systems. Similarly, if you look at smart actuators and sensors, they are all, for example, today you have normal process control valves. You have smart valves which can first of all which contains loops which have digital controllers for positioning valves, drives, power electronics. It has not only that, it has software which can do online calibration, or it can do diagnostics, etc. It can signal failures. So all these are possible because of the presence of embedded electronic systems with the valve, which are field mounted and directly present on the valve itself. Similarly, you can have smart sensors, as we will see that we are going to have sensors which can directly connect to digital communication networks and can transmit their values to a remote operator interface or to a remote controller. So such smart sensors, the typical architecture is shown. So here you have the real transducer. Maybe let's say it may be an RTD, and this may be the signal conditioning and processing circuit for RTD, which may be a bridge, and then this analog signal out of the bridge is going to be interfaced to some application processor, which will do two things. Firstly, it will take this signal and then maybe do some signal processing and maybe put it into maybe do some linearization and other things digitally for the signal processing, and then finally that's one side of it. The other side of it is that it will be able to transmit these values on the network. So it will make this whole sensor or the RTD will become network compatible, in the sense that it can directly communicate its readings into the network. So such a thing is called a smart sensor, and it's basically possible. Basically, this part of it is the conventional sensor. After that, you have, this is the embedded system which actually makes it a smart. Similarly, if you have distributed process control system solutions, so there you have, you can have a various kinds of architectures. Here is an architecture where you have IO field IO connected to remote IO racks, and these remote IO racks will take a number of field IO channels and then will transmit them over networks. All the green lines are actually computer communication networks, and similarly they may communicate it to some local controller, or sometimes the local controller may again in turn communicate to a remote controller. And so all these things, so each one of these things actually contain various kinds of cards, which are actually microprocessor based cards, and which are embedded, which have some embedded computational electronics in them. So they make possible the coordination and transmission of variables. I mean, the large amount of data can be made available to all over the place in the factory for possible use in for improved coordination and efficiency, etc. So similarly, when you have flexible manufacturing systems, basically essentially it's coordination. So you have all these embedded systems. So basically you see that once you have local systems which have computational capability in them because of the embedded electronics, then one can easily think of the next step would be to think of communication of digital electronic communication between these so-called smart devices, so that they can coordinate amongst each other for improved performance, right? So flexible manufacturing system is exactly that. So here you have a concept of a work cell where you have these computer controlled machines, you have these smart automated material handling systems, you have robots, and depending on the batch that you are processing, they can be always reprogrammed, and they can do various kinds of function in very efficient manner under the coordination of a computer, right? So that is called flexible manufacturing. So what we see is essentially that similarly, these manufacturing system components used, vision systems, automated material handling, robots and things like that. So basically if you see, then one of the strong trends in industrial automation is firstly to have more you have devices which can perform, devices for sensing, actuation as well as control, which are more sophisticated, which use more complex control algorithms, which can which can monitor themselves, calibrate themselves, diagnose their own health, etc., which are all possible basically by in situ computation using on device electronics, computing electronics processors. So which are basically called embedded systems, and then so these enable you to take real time decision, and these devices are also communication enabled. So once you have these, then locally you have a lot of intelligence and lot of computational tasks can be performed locally, and then finally you can, once you have these smart systems placed or all over the factory, then it becomes very simple to integrate them both in the horizontal level across the factory as well as vertically, from between planning and design to manufacturing execution systems down to the automatic control levels. So you have a vertical integration which we have seen in the automation pyramid, as well as you can have very great horizontal integration using networks that is all over the factory at all the levels can be integrated, which is possible through networking. And in the next two lessons of this course we are going to talk about such an industrial communication network called field bus. So as we see that basically in this lesson we will be talking about embedded systems which enable a lot of real time decision making and intelligent sensing, actuation and control, and these in turn act as enablers for integration using communication technology. So in the next three lectures in this lesson we are going to learn about embedded systems. In the next two lessons we will learn about one industrial communication system called field bus. So what are embedded systems definition wise? There are a variety of definitions, but very simply stated, an embedded system is a special purpose computer built into a larger device. It's called embedded because, for example, if you look at this, you are not probably able to see, but let us say this is a computer screen, right, and I have a PC just below me which you cannot see. So this PC is not an embedded system because it is a standalone computing system. It is a system only for computation. But for an embedded, but imagine a processor which controls, let us say, to give you a very simple example, a washing machine. So that is also a computer. There is also a processor. There is memory. There is, in principle, that processor and this processor are quite similar. But that is called an embedded system because first of all that's a very special purpose computer that's built just for controlling the functions of the washing machine, and it is built into the washing machine. So it is embedded inside it, so you cannot as such see it unless you really open it out, and it works from within a larger device. So we call it special purpose because it is built solely for that purpose, while this PC is actually a general purpose computing machine and could be used for a variety of functions including control, various kinds of display, storage, general computation, communication. So PCs have been used for all kinds of functions, while these are very specific application specific devices, and it's a part of a larger device, right. So that's a very general and simple definition of an embedded system. What do they contain? They are actually processor based systems. So they generally contain a number of processors. They can be various kinds of they can be microcontrollers, they can be microprocessors, they can be special purpose processors like digital signal processors, etc. and they now obviously contain program and data memory. All microprocessor based systems contain that, and they contain special circuitry because these are systems which are typically built for interacting or responding to the environment. So they get a lot of signals from the outside world, and they also give out a lot of signals to the outside world. So input output is very important for them, and input out, there are these outside world signals, when they will come, and that's not known. So therefore they have different mechanisms of communicating. Interrupt is one of the mechanisms which we'll see. Time is very important in most of these systems, because many of these control tasks are actually time oriented, that they have to be, once they start, they have to be finished within this time, or once somebody demands some kind of value, it has to be given within some time. So there are some timer circuitry required. Similarly, since they communicate with they have lots of communication requirements, so they are generally they support some communication interfaces. They are sometimes very critical components in systems, so they have to be tested, and they provide test interfaces. Sometimes they require human operator interfaces, like various kinds of displays, so they need human interface, device interfaces. These are the kinds of interfaces that they have. Sometimes they have some application specific ICs which are called ASICs. Sometimes they contain reprogrammable ICs like FPGAs, CPLDs, and things like that. Things where the IC can be programmed by software to behave like a particular application specific hardware. They obviously contain buses. Some of the buses are special purpose buses, particularly designed for specific embedded applications. And in terms of software, they contain a real time operating system running in them, and finally they contain the application programs or the tasks. Okay, so these are, if you take a typical embedded system, you will find many of these. You may not find all, but you will find many of these in an embedded system. For example, let's say this is a particular 8096. This is a slightly old processor which was designed for embedded system applications, and if you see it, you will see that it contains many things which are required for embedded applications. Like for example, it contains this is the processor. This dotted part is actually a processor. It contains this basic processing, as well as it contains a register file. So see, it contains analog to digital converters and analog multiplexers, so that this chip can interface with analog signals. It contains a lot of ports. It contains a serial port. It contains parallel ports. It contains timers. See, timer 1, timer 2, and watchdog timer. It contains on-chip memory, that is at least for building small scale applications, you don't have to interface this with external memory. Excuse me. But you have also been provided facility to interface with external memory if you need to through these ports. In fact, this system is somewhat configurable in the sense that if you need memory, this can work as memory interfaces, address and data buses. If you don't need them, then they can just work as ports. Similarly, if you want this chip to drive some power electronic actuator, then you often need a very clean pulse width modulation signals that we have seen in the power electronic drives, that many of the motor drives actually require pulse width modulation signals. So this has a pulse width modulation circuitry on chip which can actually generate this signal through this port. So you see that this is a typical processor. Nowadays you have higher, these processors can be of various complexities. In the embedded system market, you have processors from 8 bits, 16 bits, 32 bits. So you have lots of various kinds of processors. So this is a typical an embedded system processor. Now if you embedded systems typically for various reasons, I mean actually embedded systems for industrial automation are somewhat well behaved, in the sense that embedded systems are required to be sometimes working under, there are various other kinds of embedded systems which are other than embedded systems for industrial automation, right? Like let's say if you have a digital camera, that also contains a processor and that has an embedded system. If you have a watch, it can have an embedded system, right? So so many times these systems actually work under constraints of CPU power. In the context of industrial automation, people generally use speed may or may not be such a constraint. So people often use chips which do not have very high clock speed, because in the name of reliability. There may be memory may be scarce. Power consumption is often a very important consideration, because if you have to continuously replace, many of these systems are battery operated, and therefore to increase battery life, power consumption is very important. Sometimes they don't have so many peripherals and they have slow buses. Then since some of these systems actually must be very small, since they actually have to embed themselves in small devices, so they work with size, weight and sometimes environmental reliability constraints. On the other hand, they have very big performance goals. Like, first of all, they have latency bounds. They are since they control events, so it is generally preferred that their response times to the signals that they receive from the environment are actually very important, and it is often desired that these response times are bounded. They need to work with very high reliability, because they often control machines which can, where if they malfunction, they can create sometimes havoc. And they must be interoperable, in the sense that they have to work with variety of various kinds of devices manufactured by various types of companies. So they must work with must follow some common standards of operation. These are typical requirements which embedded systems have. Now coming to, I thought that we should take a look at the basic principles of input output which the embedded systems support, because input output is a very important function of embedded systems, and as we know, those who have studied microprocessors will know that input output devices, isolated devices, can be interfaced to the CPU in generally two ways. Either it looks to the computer like a memory device, so it simply, just like it reads a data from memory, it can read a data from an IO device register, simply like a memory read or a memory write. Or sometimes they are distinguished, that is, memory device and IO devices are distinguished, and their address spaces are also different. So whether it's a memory read, so memory read writes and IO read writes are sort of separated out, and they are distinguished by this memory IO line. So if it is high, then people think it is memory. If it is low, people think it's an IO port. So in both cases, this kind of input output requires that the CPU itself has to read write data. So they are generally used when small volumes of data are to be transferred from devices infrequently, like AD converter readings. So at a time you get only one reading, so an AD converter is generally interfaced in this manner. On the other hand, there may be other situations where devices need to transfer large amounts of data, so, or they may be external to the main processor system, in which case people use bus based input output. So you have a bus to which you connect all the devices. So now this bus, which is nothing but a set of conductors, electrical conductors, basically some lines, they are all the devices are connected to the same buses, right? So therefore obviously a bus is a shared resource. So I mean everybody cannot, Reading writing means what? Reading writing means applying voltages to these lines on the bus. Now if everybody simultaneously starts applying voltages on these lines, then all these voltages will interact and all the data will get destroyed. So therefore there must be some way of there must be somebody who has to decide that who will talk, who will use the bus at what time. So therefore there is usually a bus master who will allocate the bus to various others who are called, just to distinguish them, they are called slaves for communication. And similarly, for once, since they have to communicate and then everybody is connected, so therefore there has to be ways of knowing, ways of telling that what is this communication for, who is it for. So there are elaborate rules by which, following which this communication takes place between the transmitter and the receiver, right. So they are called protocols. So in many cases, while some of the devices the CPU directly interacts with them as if it is a component of its own system. Sometimes for other devices, one needs to set up an external bus according to some standard protocols, like say AMBA is a bus which is used for embedded systems. So some protocols, and then they connect, people make devices according to those protocols. So people can put together embedded systems where the CPU and the devices follow such protocols and communicate. If you extend this concept, you can also have networks where the buses are actually geographically separated. Here still this bus will possibly be housed within some some mechanical cabinet or something, or maybe some slots. But if you extend the same concept, then this bus can become a network bus, and then it will be traveling for kilometers, and in the same way devices will be connected to them, and they will also communicate according to some protocols. So this is so basically bus based communication is actually very common. Now bus protocols typically are either synchronous or asynchronous, in the sense that sometimes the exchange of data occurs in distinct steps of time according to some clock. That is useful when in that way, when a large volume of when a regular transfer of data takes place and both the sender and the receiver can actually work at the same rate, then in such cases these synchronous bus transfers are useful. On the other hand, in some cases transfers bear no timing relationship when they are only event related. So after somebody raises another one line, places the voltage on another line, then another device reacts and he will read something and then will place another, maybe some data acknowledge signal, it will pull low. So everything is actually, so all the actions take place with respect to events which are occurring on the bus, and not with respect to some well-known, some well-specified clock. So such bus transfers are called asynchronous, or sometimes they may be semi-synchronous, in the sense that some of the control activities may be asynchronous, but within the control activities, when large amount of data transfer takes place, then it can be synchronous. So they are called semi-synchronous, or basically uses both synchronous and asynchronous technologies. So these are basic principles by which data transfer takes place, and there is another very important concept of interrupts. It turns out now suppose that there has to be, the CPU is actually all the time doing calculations, various kinds of calculations, and now it has to do calculations as well as it has to do input output, in the sense that it has to read signals. Now while it is doing, and it is doing many calculations, so various kinds of calculation. So how does it know when it needs to read some signal, whether the signal is there or not, right? So so there has to be a mechanism by which other devices can tell the CPU, which is actually busily doing some calculation, that now there is some signal available here which you need to read and use in the near future possibly, but now the signal is present, please read it. Please leave your calculation for some time come and read this signal, and then you decide whether to work on this signal or whether to go back to your calculation, right. So basically this is achieved by what is known as an interrupt. So while the CPU is doing something, the interrupt is actually a mechanism by which external or internal events can change the course of program execution. So the program execution is going on serially, and then if an interrupt comes, for some time that program execution thread will be stopped, and the CPU will do something else, and then maybe depending on the logic it may either come back to it or may start some other thread execution, right. So the way this is inbuilt into the CPU hardware. The CPU hardware is built in such a manner that it automatically responds to interrupts, and such interrupts are called hardware interrupts. Similarly, such things can also be done by sometimes by executing some software instructions which are called software interrupts. And then once interrupts arrive, this interrupt service routine, there is a piece of program which gets executed, that is called the interrupt service routine, which handles the system interrupts. And then there are ways of various interrupt service. You can understand that while an interrupt service routine is going on, another interrupt can also come. So one has to decide that which interrupt is actually more important and which interrupt is less important and things like that. So there may be, so in these interrupts can also have their own priorities, and accordingly their responses are decided. But since the system is all the time going through interrupt, and since interrupts are such important things that the CPU will instantly leave what it is doing and at least take a look at what interrupt is there, it is so important. Therefore these interrupt service subroutine responses must be very quick and absolutely predictable. It should not happen that some interrupt is coming and that interrupt processing can take a lot of time. Then the system response will never remain predictable or bounded. So therefore all care is taken such that people can write interrupt service routines with bounded delays. So interrupts are very highly used things in embedded systems. Now this, after the hardware, so now we have got this hardware with various processors and with various input output devices and these interrupt mechanisms and memory, right. So now we have to use this piece of hardware and put programs in them such that they can do some meaningful work. Now obviously this software, so now the softwares will actually achieve the various functionality that is possible from embedded systems, and typically embedded software has certain properties, like for example they have to be timely, in the sense that their executions must be related to times, that they must finish within certain times, or they will occur with certain regularity of time. So they are very related to time. That's why they are sometimes called real time. Then they require concurrency, in the sense that there are several tasks, all of which need to be processed together. So it's not that, but at least it should virtually be together, although strictly speaking it's going to be sequential because there's only one processor. But it cannot happen that, so all of them must be processed together, right. We cannot, because suppose one computer is monitoring 5 control loops. So naturally the programs of these things must occur. So this control must go on concurrently by very fast time division multiplexing, sometimes this, sometimes this, sometimes this, and then come back to this. So virtually you think that all the works are being done. Then the liveness, that is, the situation should not occur that everything stops in the computation, always something should go on, right. Then there are various, it must handle various kinds of interfaces to various kinds of devices which are very heterogeneous, and they must be reactive to the environment. That is, when certain conditions, that is, so mechanisms of interrupts etc. must be present. I mean the software must handle these things. So these are some properties which typically embedded system software must have, and that's why these softwares are generally called real time systems, because they are generally concerned with time, and they are generally real time systems are not necessarily, but generally real time systems are reactive and concurrent. So, so what is a real time system? So, real time system is a system where correctness, that is the functional correctness, that if suppose if you give you a program which let us say calculate, let us say that 2 control algorithms. So, one control algorithm may be very advanced and maybe calculating very good control, but if it cannot calculate within a sampling time, then that control algorithm is no good. So, it's not correct. That solution to the embedded control problem is not correct. That embedded control program, it may employ very sophisticated algorithm, but since it cannot compute its value in time, it's not a correct solution. On the other hand, another algorithm which may be approximate but produces a solution in time is correct. So, its correctness depends not only on the correctness of the logical result, but also on the result delivery time, right. So, a system that responds in a timely and predictable way to unpredictable means external stimuli. So, these are so real time systems or embedded systems for industrial automation must be built in such must have this as a system. It must have these properties, which is to be realized through the software. Now, for realizing this software, especially when it has to do complex signal processing or with a number of signals and a whole array of tasks, it becomes very difficult to actually, and correctness, it should not have any mistakes. So, for ease of development and for ease of running, these kind of complex RT software generally are run within an environment of an operating system. So, they generally, complex real time software generally require support from a real time operating system, which actually basically provides some services, provide some tools, some handles, some small equipment which this software can use to achieve its purpose. So, an operating system is basically has 4 main tasks. One is process management. So, there are at any time, as I am saying, that multiple tasks must be managed. So, that the new tasks get dynamically created, they have to be created, they have to be scheduled, that is, one has to decide when to execute which task, they have to be loaded onto the memory. Finally, while they are executing, one has to keep the control, they have to be terminated, removed from, all sorts of things have to be done. So, that all these related to tasks are called process management. Then there has to be inter-process communication. These tasks are actually not unrelated. So, they are quite related and they will exchange data. So, the result produced by one has to be used by another. So, all kinds of synchronization are necessary, data exchange mechanisms are necessary among tasks. So, the operating system provides mechanisms by which application programs can actually do that. They provide process protection, so that one process does not corrupt the data of another process, right. Similarly, it provides memory management. So, some task requires how much memory it will require, what will be the address space. So, all these things. Similarly, input output management. So, these are some of the crucial low level functions which the operating system provides. So, using these features, one can write programs which will use these features to quickly develop correct and efficient solutions. Apart from that, a real time system has some special features which help to develop real time. Real time operating systems are required for developing real time systems. So, it will have some features such that bounded behavior can be realized. So it's not that if you ask for another 1 kilobyte of memory, then to get that 1 kilobyte of memory, you can sometimes require 1 millisecond, sometimes require 50 milliseconds. You get this sort of things, or you try to access one particular variable. So, sometimes you get that variable value within maybe microsecond, and sometimes you get it, you don't get it in several milliseconds. So, if you have this kind of mechanisms, then your system response, there will be no predictable behavior. You cannot predict the behavior of your programs in a real situation. So, real time operating system ensures that it is possible to build predictable programs. But at the same time one must remember that an operating system mainly provides some computational service. As such, it cannot ensure that your application is right or it will work in the proper manner. That is to be designed by whoever is designing the system, but the operating system merely provides an environment in which it is easier and possible to develop this. Now, real-time operating systems necessarily have to be multitasked, because all the tasks, I mean every task has to be performed. First of all, tasks are sometimes repetitive and they have their own time deadlines, and therefore very good utilization of the CPU time needs to be done. So you can see that here what we are showing is that typically computation is input output. It goes through a cycle of computation and input output. Now, while input output is going on, in many cases the CPU need not be busy, so it need not be idle also, right. So therefore it makes good sense to say that if one task requires some input output, then let it do the input output while the CPU can use this time, because input output devices are also generally slower than the CPU. So by the time some 1 kilobyte of data will get transferred, the CPU can do much more computation. So it should switch, it should keep this task in store while it is waiting for IO, and then go to another task and then do its computation. That is better utilization of time. So such a thing is called multitasking, and it is extremely important for real time systems for the best utilization, so that good timing deadlines can be achieved. So under such a multitasking scenario, every task in its life cycle, it goes through several phases. Like for example, when the task is first created, it is created, so it's called new. Then it is admitted into that is ready to execute. Some memory space has been allocated to it, etc. Then it is ready. Then it's put in some sort of a queue where it is put in where it is called ready. So now it is ready to be executed. Now some task is running, and now while it is running, so many things can happen. Either the task can go for an input output. So if it goes for an input output, that running task is now put as a is removed and put into a waiting state, because it is now waiting for an input output or event. So once it is waiting, now immediately there is some part of the operating system will now decide that during this time while this task is waiting, which task will run. So from among the ready tasks, this processor, this scheduler, or some part of the program which is responsible for this scheduling will take one of these tasks and make it running. Now while this task is waiting for, this old task is waiting for IO, after some time the IO will get completed. So when it gets completed, then it will move to the ready state, right. So it will be moved to the ready state and then it will be waiting. So on the other hand, one task may finally get terminated. So once it gets terminated, then again the scheduler will look at the ready queue and see which one it has to schedule, or there may be some interrupt coming. So if the interrupt comes, then immediately the scheduler goes to see the interrupt and then see that after it does some part of the interrupt processing, it decides now what to do. Should it go back to the original running task, or should it schedule some new task, or should it do some computation related to the interrupting task. So in other words, what I am trying to say is that always a task goes through these kind of states. So it becomes ready, then it goes through this cycle, this ready, running, waiting, ready, running, waiting, or sometimes it executes ready, running cycles, and then through this its computation goes on, and then finally it terminates itself. When terminates itself means when the computation finally finishes for that task, then it may exit. So, this is a typical computational task life cycle in the embedded system, right. Now, similarly, so this was about process management. Then memory management, embedded systems have some typical things like, for example, memory access times, as I said, should be predictable. So there is a mechanism of virtual memory where because of shortages of RAM, there is a strategy by which you have a concept of virtual memory. So a process, so if an address is not found in if a particular variable is not found in the RAM, then there is a mechanism by which you can access the disk and then find it out. So you can have a much, since the disk is slow, but disk has a much larger memory space. So the address space that you can use in your program can be made very large. So this is called a virtual memory system, but embedded systems often prohibits the use of virtual memory systems because they can make a memory accessible memory access very unpredictable. So if it is in the RAM, it will be fetched in microseconds. If it is not in the RAM and if it goes to a disk, which is an electromechanical device, then it can take several milliseconds. So for that, they sometimes say that virtual memory should not be used. Similarly, static memory allocation, that is right in the beginning, programs whole memory is allocated. It is not that dynamic memory allocation means whenever a program needs memory, it will be given some memory, and if when it does not need memory, memory can be released also. Now these strategies are, in terms of memory utilization, they are good. Static memory allocation is actually expensive, but at the same time, sometimes it may happen that some peculiar situation may arise in which one task is actually asking for memory but is not getting it because there is no memory in the system. So if you have dynamic memory allocations, then such things can occur right in the middle of execution of a task. If in static memory allocation you already take worst case and then provide for enough memory, of course your system costs will increase. But for embedded systems, since they control much bigger systems, so such costs are generally not problems. So therefore, dynamic memory allocation is sometimes avoided in the case of embedded systems, or even if you have it, then you must provide for situations that if there is a memory allocation failure, then what is going to happen. So you must be prepared for these strategies at runtime. So such features are there for memory management. Similarly, interrupt response. So various systems have various interrupt response. So when an interrupt comes, first the interrupt is coming, then the interrupt service subroutine is, the control goes to the interrupt service subroutine. Then in the interrupt service subroutine, one sees what are the other pending interrupts, which interrupt should be executed. Then sometimes some interrupts are so important that temporarily what one has to do is that it has to disable interrupts in the sense that there are some parts of the code which are called critical sections which must be executed continuously. So one must ensure that no other interrupt will come while that small part of the code is getting executed. So before that code execution, the preemption is disabled, that is control cannot be preempted, those tasks will serially be executed, and then so these critical sections are executed, then some scheduling decisions are taken, and then finally after this scheduling, a decision is taken as to which task is going to run now. So then the content switch, that is content switch means one task was running, so all its registers were actually loaded with the values, so they have to be stored in the proper locations or stacks, and then the next task which has to be run, their values have to be loaded. So this is called a context switch. Actually this is written as content switch, that's wrong. It's called a context switch, and then finally it will return from the system call. So all these things happen every time an interrupt comes, right? And one of the steps, as we have seen, of this interrupt responses is the scheduling decision. So now every time this scheduler is invoked, scheduler is again a program. Every time a scheduler is invoked, the scheduler decides that which task is to be run. So, as we have seen during the life cycle, that CPU scheduling decisions can be taken are continuously this scheduler examines. So, suppose the task switches from running to waiting state, that is, it is waiting for some IO or some event. So, then it will execute some software interrupt by which it will tell that I can wait now, I am waiting for IO, and let the scheduler decide which task to run. So, during this time the scheduler can switch this task out, it can do a context switch and put another task and then execute it while this task is waiting. Similarly, some such switches can happen when it is going from running to ready state, that is, if another interrupt comes, every time an interrupt comes, the scheduler is invoked and the scheduler again takes a look at the ready tasks and their priorities and their importance, and then decides which one is going to be run now. Similarly, if some such task goes from switches from waiting to ready after an IO event completion, then also it can be. So at various points of time when tasks are executed continuously, periodically the scheduler takes a look at the ready tasks and then decides which task will be run now, right? And for scheduling, scheduling is very important. Like, for example, there are two tasks here. Now, task 2 takes 5 time units for execution, but its deadline that it should be completed after a long time. This is the deadline for task 2. While task 1 takes this much amount of time and it has a deadline of D1. So, obviously, if you execute task 2 and then try to execute task 1, then the deadline of task 1 will be violated. So, task 1 could not complete by its deadline. That's a fault. On the other hand, so obviously this is a trivial case. Obviously, you should execute task 1 first so that it meets its deadline, and then execute task 2 so that it also meets its deadline. So, this is the correct solution. So, you see that scheduling is important, that is the order in which these tasks are going to be executed, right. So, there are several scheduling techniques which can be used. One of them is, the simplest of them is the cyclic executive. So, this says that you have n number of tasks and simply go on executing them in cycles. So, first do task number 1, then 2, then 3, then 4, then 5, and come back to 1, right. So, cyclically execute these tasks. Now, this will be possible when the number of tasks are fixed, when they can be cyclically executed. But there are several situations when tasks can be generated in response to events, So, then we cannot execute them cyclically, and we have to, sometimes tasks will be generated, sometimes tasks will be terminated. So, for such event driven situations, you can have two kinds of scenarios. One kind of scheduling is called non-preemptive scheduling. That is, you actually decide in what order to run these tasks, but once you have started one task, you actually complete it, and once it's completed, then you again decide which task to run. So, you don't preempt a task while it is being executed. That is called non-preemptive, but as it turns out that again cannot give you the maximum amount of flexibility, right. So, the strategy which is actually used for embedded systems scheduling is preemptive scheduling, right. So, in preemptive scheduling, every time, the moment you have a higher priority ready task, the execution of a lower priority task is going to be stopped and the higher priority task will start. So, the task execution can be preempted at any point of time. Now, this priority business, how you are going to assign priority. So, there you can have a static method or you can have a dynamic method. So, if you have a dynamic method, so you can have two protocols, right. So, we have one protocol is rate monotonic, which says that tasks which have rate monotonic protocol is typically applicable for periodic tasks. So, it says that if a task has a lower rates at which it is going to be executed, for example, here the deadline is 5. So, it is going to be called once every 5 units of time, while D2 is 7. So, it is going to be called every 7 units of time. So, this task task 1 is actually more frequent. So, therefore, it is more priority, it is more important because it is more frequent. That is the strategy that you do for rate monotonic scheduling. So, you see that what is happening is that first suppose task 1 and task 2 are both required. So task 1 is computed. Since one is higher priority, it will be done. Then 2 gets executed, and since 1 is not called, now here 1 is executed. See, 2 has not been finished. 2 requires 4 units of time, that is computational time C2, while this is 1, 2, 3. But then task 1 was again called, because now it's 5 units of time. So the second call of 1 has come, therefore 2 has been stopped. So in this case, since the priority is fixed, 1 always has higher priority. So every time there is a requirement for computing 1, 2 is being stopped. So this is the execution cycle, and we can see that we can with these 2 tasks we can actually meet their deadlines, right. So this is called rate monotonic scheduling, which is generally useful for a fixed number of periodic tasks. On the other hand, for greater CPU utilization, there is another strategy which is also employed, which is called the earliest deadline first strategy, which says that here the priority is not fixed. Here the priority can keep changing with time. So whichever task has a closer deadline now has higher priority. So right now 1 has a closer deadline, so 1 has higher priority. Now after that 2 starts executing. Now here you see that 2 will be again called at 5, but now the deadline of 2 is later than the deadline of 1 is later than this deadline of 2, so therefore 2 will continue to work, because at this time 2 has higher priority because its deadline is earlier. So this is the difference, and it can be shown that you get better CPU utilization with this strategy. So this brings us to the end of this lesson. So what we have seen is that in this lesson we have seen applications of embedded systems in industrial automation. We have seen the typical hardware components that are present, processors, memory, various kinds of I/O, and we have seen the characteristics of embedded software, that they have to be timely, they have to be concurrent, they have to be reactive, and we have seen that generally you need, for ensuring building right systems, you need real-time operating systems, and we also took a look at real-time task scheduling. Now you can have several questions, like you can have your own example of an embedded computing system and find one that is not, or again if you get an example of an application specific processor, if you see the net, you will find these. You distinguish between hardware and software interrupts. Any microprocessor book will give you this answer. Name 3 strategies adopted by RTOSs to have predictable response times. They have been mentioned in the lecture. And name 1 advantage of EDF scheduling compared to rate monotonic. So rate monotonic is preferable for periodic tasks, and EDF has better CPU utilization. So that's all for today. Thank you very much.